Can you click got it, Matt? And we'll do the recording. Hi, everyone on YouTube. Welcome to the seminar. We'll get started in just a moment. Got that one too. And all right. So welcome everyone to our next water, wetlands, and watershed seminar for fall 2023. Today we are continuing in our semester of celebrating the 50th anniversary of the Center for Wetlands, which was started here in 1973 by Dr. Howard Odom. We're having all alumni from the center come and present, and these alumni stretch from different decades. And so today we are lucky enough to have Dr. Matthew Cohen as our speaker. Matt Cohen has his undergraduate in environmental engineering from Swarthmore University and his master's and PhD both here from the Center for Wetlands, where he worked with Dr. Odom and with Dr. Brown for his master's and his PhD. Dr. Cohen is a professor in the School of Forests, Fisheries, and Geomatics Sciences at UF, and has just had if I can use the word, an illustrious career trying to figure out how ecosystems and hydrology interact. And so any ecosystem that Matt begins to study, he unpacks and unravels from the Everglades to springs to forests. He's been recently on on ice sheets in Greenland. I'm really trying to understand the ecohydrology and interactions between ecosystems and ecology. And the hydrologic system. So today we're going to hear about a very iconic system that you've been working in for 10, 15 plus years, Florida Springs. And we're really lucky to have Matt at UF and as the new interim official interim director of the UF Water Institute. So congratulations on that. And the floor is yours.
Thank you. Yeah, I spent a lot of time in this room as a graduate student. And it really just hasn't changed. But the blinds are a little better, the projector's a little better, but
You got new furniture.
yeah, the chairs are a little better. The spirit is the same. And so yeah, what I wanted to talk about today is work that is ongoing in my lab. We've been thinking a lot about this phenomenon that happens in the springs of the Suwannee River, where the black water of the Suwannee River under high flow pushes the springs water back into the aquifer and does a host of things that we think are super relevant to understanding the state changes that we're observing in those ecosystems. And that therefore should sort of merit the attention of our regulatory agencies if the incidence, duration, frequency, severity of these things that we call reversals are increasing. I'm going to acknowledge a bunch of people by citation throughout the talk, but two people in particular, Paul Donsky, who's in the room somewhere, there he is, and Sam Howley, who's another master's student in my lab, who's not here because she's frantically trying to get her thesis defense slides made, but both of them have been super instrumental in all of this stuff that I'm going to present today. So let's just start a little big picture. There we go. So we know that rivers gain water. We know that they lose water in some reaches. And there was a recent synthesis by Scott Jasechko, who's at University of Calgary, where they basically interrogated the elevation of the water in millions of wells around North America, vis-a-vis the stage in the river that it's adjacent to, and identified these quite intriguing patterns of where rivers are systematically gaining, which are the blue colors. That is to say, flow is coming from the adjacent groundwater and moving into the channel versus where water flow is being lost, which is to say that the river is actually subsidizing the adjacent aquifer. And so what we get are these situations where the flow is gaining when the groundwater is above the river and flow is losing when the groundwater is below the river. And you can see patterns, right? There's some interesting patterns, for example, in the Sierra Nevada, where the high mountain streams are gaining. And then once you get down into the alluvial valley, they become losing. Florida doesn't look very interesting in this regard, but the basic idea that rivers kind of populate this gaining and losing situation, I think is really relevant. And the Suwannee River is an interesting, maybe infinitely interesting special case. So we'll talk a little bit about that. So this picture, Jenny Adler, who's a photographer here, now photographer with National Geographic, chronicled these junctions between these two very, very distinct types of water, right? The dark, acidic, usually warm, oxygen-rich water of the Suwannee River, and the clear, alkaline, constant temperature, often very oxygen poor water of the Floridan aquifer. And where they mix, you have these beautiful mixing zones with these billowing clouds of stained, of tannic staining. And that's a pretty typical condition at the confluence of the spring run and the river. And so in typical conditions, the aquifer stage is higher than the spring pool. So water is spontaneously discharging there, and it runs down a spring run and discharges into the Suwannee and creates these mixing zones. But from time to time, the Suwannee River will stage up. And when it does, that staging up, it stages up very quickly, far more quickly than the Floridan aquifer. And the stage in the Suwannee River actually compress water back into the Floridan aquifer and create conditions where the spring run is much deeper for a time, much darker for a time. The velocity goes to zero, sometimes goes negative, right? Water will be pressed up into the aquifer. Why does this happen? Mostly it happens because the Suwannee River and the Santa Fe River have this sort of weird dual personality thing going on. On the one hand, they have regions of their watershed that are confined. That is to say, there's a geological confining unit that keeps the raindrops near the surface. When it falls, we get a lot of wetlands, a lot of streams. When it rains, that system generates floods very quickly. So it's very fast rainfall runoff response. So that creates flashy black water conditions because it's interacting with a lot of organic matter, a lot of wetlands. The lower basin, on the other hand, is unconfined, right? So there's a boundary between the two, which is called the Cody escarpment. And the lower basin, the unconfined region, a very slow rainfall runoff because basically the aquifer rises extremely slowly and it's vast. And so it takes a long time for that pressure wave to propagate out. And so we have these situations where the floods from upstream can propagate down and cause these reversals. There's a lot of ways we can sort of diagnose this. So for a couple ways just to sort of visualize the consequences of this, I've taken all the gauges that are in the upper basin, right? There's 3 of them. I'll talk a little more about that in a second. And then 3 gauges along the length of the Suwannee. And you can see this is the mean discharge, and it goes up over time, over distance, right? The discharge is increasing. But if you look at the size of the error bars, they're declining, right? The variance in flow is declining as I go from the uppermost parts of the karstic Suwannee River to the lowest points. And so if I do this is the coefficient of variation. The coefficient of variation is more than cut in half. So the variability of flow is really high in the upper part of the river and is dampened as it goes down through. Why does that happen? It's because basically the banks are absorbing huge volumes of water during floods, which means that water isn't flooding further downstream. This happens even more markedly in the Santa Fe River, where we compare the confined part, the Worthington Springs gauge, with the 4-white gauge. Another way to visualize this.
Well, we may be running low on battery on the clicker, so you can. Yeah.
There it is. Yeah. All right. So if we look at, wow, that one came out weird. If we look at the flood size as you go downstream, so this is a typical flood interval plot. So this is basically the occurrence interval of a flood, and this is its magnitude. So this would be out here would be the 100-year storm. This would be the 50-year storm, 50-year flood. And what's happening is that the size of the floods is getting smaller as you go from a 15,000 square kilometer watershed up to nearly a 25,000 square kilometer watershed. So you can increase the watershed area by 10,000 square kilometers, and the size of the 50-year flood has been cut in half. And that's basically because there's this incredible bladder that fills up adjacent to the Suwannee River. When it floods, the water gets pressed out into the banks, it gets stored there for a little while, and it comes back out. So there's this large reservoir that is quite atypical for rivers, but super important for understanding the Suwannee. This is really important for lots of reasons. One of them is the genesis of all the caves that people like, over the cave diver, they swim through, which I think is Jason Gully, who was your advisor, right? Has written a really cool paper about the origins of these caves. And the idea from the sort of conventional karst literature is that the caves formed because slightly acidic rainwater was percolating down and etched out the caves incrementally until it got to the Suwannee. What Jason pointed out by looking at the shaping of the scallops on the walls of these caves was that they were really being formed by acidity that was being pressed in the other direction. The normal flow direction is like this, but all the scallops imply flow into the aquifer, and that's where the caves are generated. And that's because during these flood periods, the water that would ordinarily be in the aquifer is oversaturated with respect to the aquifer minerals, the media, And as soon as the floods come, they're super acidic. So they start to etch away the spring. And one paper, John Martin, who was Jason's advisor, estimated that a single storm dissolves somewhere on the order of 30 cubic meters of limestone around Madison Blue Spring. And so it's a contemporary process, and it's what's making these caves big enough for people to swim through. So there's a sort of geological reason why you might be interested in this, but there's a lot of ecological reasons as well. So first of all, this brown water radically changes the energy budget of a spring ecosystem. It alters the light regime dramatically. It's pretty clear, and it does it for two reasons. It does it because the water is deeper, and deeper water just extinguishes light more, even for no change in clarity. But if it changes the color, the extinction coefficient on that is accelerated. And so often you'll get situations where during a flood, the benthic autotrophs, the plants, the rooted plants, the algae, they're getting zero light. The lights completely turn out during this reversal process. It lowers the pH of the water. And if you're a shell-forming organism like a gastropod, a snail, that can be really problematic for you. And so because snails are the core controls on algal biomass, one of the core controls, this can be important, have a sort of trophic cascading consequence. The reversals also add a lot of dissolved organic matter to the system. So we've just added energy to the heterotrophs as well. So all of a sudden they have a lot of extra food. It alters the metabolic balance because by turning the lights off and adding organic matter, we're basically altering the carbon budget, the energy budget substantially. So sediment, and because the oxygen budget of the system, if I've heard anything I've ever said about springs, it says oxygen really matters. You guys can leave now. But the oxygen controls a lot of things. One of the things it controls is the redox potential that's in the sediments. When under oxygenated conditions, the SAB experience high redox sediments, and they grow really well. And when we deoxygenate the sediments, we tend to kill the SAB. So we have this low pH, darkly stained water contrasting with the high pH, unstained water. And a recent experiment, this is Greg Owen's master's thesis, showed that when we oxygenated a tiny little piece of Hornsby Spring, which is a spring that is basically hypoxic all the time, we added oxygen to it, it just went bananas. I mean, it completely changed. This is the growth rate under the anoxic conditions of the submerged aquatic vegetation. So basically planted them and they all died. But the growth rates under oxygenated conditions, which are all the red dots, plants thrive. And when we did both adding oxygen and adding grazers, the system went crazy. And the super unfortunate thing is as soon as we turned off the gas pumps, everything died. And so oxygen is the keystone variable for understanding all of these features, and all of these changes affect the oxygen budget. Sam Howley has been trying to study the oxygen in these springs. What happens during the reversal? So there's three graphs here showing reversals, a very modest flood that just raises the stage. And you can see this is the oxygen trace, this is the carbon dioxide trace. You can see the oxygen declines in concentration. That's evidence that there's greater respiration happening. The amplitude declines ever so slightly, which implies less primary production. Here's a much more significant flood where actually the spring was mixed, the brown water mixed into the spring run, so the spring was dark. And you see the system for more than a couple of weeks went completely hypoxic, right? It was zero oxygen in the system. And the amplitude went to zero. The amplitude of diurnal variation, which is evidence of photosynthesis, basically disappears. So the respiration shoots up, the primary production shoots down, and we basically radically changed the carbon budget of the system. Under an even more severe flood, this is a reversal now, where it was clear that the water was flowing upstream during the flood. There's this period of time during which it's flowing upstream that we're basically measuring the oxygen in the Suwannee River, which is pretty high. But then it sits back there, incubates for a little bit, works on the rock and mixes with the biofilms, and then it comes back out and it's hypoxic again for a long time. And the amplitude goes down, and then we see this recovery. So her thesis is about studying this. She made this graph. It's super dense. I'm not going to spend a lot of time on it. I really just want to draw your attention to this, which is across every single spring that she's monitoring closely. There's a very strong positive response, more respiration during a reversal, a decline in primary production. And so the carbon budget, which we measure based on the net ecosystem production, like the balance of primary production and respiration, is just completely crushed and altered by these reversals. And so they're super relevant to understand, because the way we measure all this is with oxygen. The there's both the direct effects of oxygen, but then the alteration of the carbon budget of the system during the time that these reversals are happening. Paul Donsky, Paul, I stole some slides from your thesis. I assume with permission. So Paul basically cruised up and down the Suwannee River and took a bunch of measurements at springs, 63 springs, I think, in the end. From a number of those springs, we have continuous records of how often they reverse. So this on the x-axis here is the river intrusion ratio, which is basically how frequently are they brown. Right, so some springs like Pot Springs are brown all the time. Little Fanning and Stutney Head Springs are never brown; they never reverse. And so there's a wide gradient of reversal incidence across the springs of the Suwannee. We can do that a couple different ways, and Paul basically showed that you can do it continuously, which are the red dots here. You can use like specific conductance, the conductivity of the water, to trace the incidence of these things. Of course, we don't have very many of those. Another way you can do it is every time the district staff goes out and takes a measurement, they look, is it dark, is it not? And you can sum that up and get a proportion. And it turns out those proportions are really consistent with one another. The relationship is really strong. So we can use the sort of low frequency data to construct an understanding of how often the springs reverse across the Suwannee. And what Paul showed is that the more often they reverse, the less algae you see. The higher the oxygen, the less algae that you see. And then there's this very strong interaction between the reversal incidence and the dissolved oxygen that I'm going to show you in a moment that leads to the conclusion that these are the two keystone controls on springs composition, the biomass and composition of the springs. That is to say, if we're thinking about restorability, if we're thinking about why we expect to see submerged aquatic vegetation or don't. So along this axis is the river intrusion ratio, along this axis, dissolved oxygen concentration, basically below 0.2, 20% of the time, springs being brown, you get SAV, and above that, you never get any SAV. You only get algae. And when the dissolved oxygen is really low, you get lots of algae, and when the dissolved oxygen is high, you get SAV. And so in terms of prioritizing where we should go to restore SAV, this quadrant is really likely to be favorable. And these quadrants out here, I think we're wasting our money. Until we solve why the river intrusion incidence is what it is, and maybe it's normal, right? It totally could be normal, but those systems probably won't support any planted submerged aquatic vegetation. So it's a really important conclusion. And it just really animates the ecological relevance of these events for the things that we care about, which are the ecological condition quality of these iconic ecosystems. Now, we've thought about this before. Bobby Hensley and I wrote papers in 2017 where we constructed what we could about the reversal incidence and what we showed. Like, so basically what you look at is the aquifer stage, right? So this is water level in a well in gray. In black is the water level in the river. Most of the time, the aquifer is higher than the river, but from time to time, the river stage is up and the aquifer is lower. We call that a reversal. There's a lot of hand waving in this because the aquifer is not that faithful a record of the reversal. It's either the well is really far away and not that relevant, or it's really close, and then when it floods, the aquifer goes up too. And so there's a lot of reasons why this is not ideal, but we were able to do it for a number of springs and sort of came to the conclusion that between the early 1980s and really the late 1990s, early 2000s, there was a strong increase in the number of these events, right? So this paper basically poses the hypothesis that change in the flow regime, the increased incidence of these reversals, is something that our regulatory agencies, the ones that design the minimum flows and levels program that is supposed to, put the kibosh on new consumptive use permits and all of those sorts of things, they ought to be attending to the idea that these flow reversals are both ecologically important and changing in their incidence. But that's not a very long period of record. And like I said, I was sort of unsatisfied, always been somewhat unsatisfied with the method. Like it works a little bit, but it's not like high confidence. But in the last year or so, we sort of figured out a way that we think we can look both further back and with more confidence at the incidence and duration of these reversals. So the idea basically is that many gauges along the Suwannee River have been collecting data since the early 1930s. Right, uninterrupted flow records from 1931 at 3 of those stations. There's more stations, by the way, that have long-term records. And each one of these, this is the White Springs gauge, the Strattonville gauge, and the Panetta gauge, they also have records dating back to 1939. So we basically have, what is that, 92 years, not quite a century, but I rounded up. So roughly a century of hydrologic data, and the flow change between any two gauges is diagnostic of the longitudinal loss of water or the longitudinal gain of water, right? So if I look at the flow difference between these two places, I can define a term called flow gain, which is positive when springs are discharging to the river and negative when the river is discharging to the aquifer. Suwannee, we basically decided that there are 4 viable segments. I'm going to show you those in a moment. So this is the unconfined part of the aquifer. I mentioned that earlier. The red line here is the mapped toe slope of the Cody escarpment. The black or the gray is the confined, where the confining unit is present. So these areas generate floods like crazy. And these areas are where the Floridan aquifer is unconfined and where most of the springs are, which are the blue dots. And so what are these reaches that we can look at? We have this upper reach, which is basically the 3 upper gauges that are right on the edge of the confining unit. So basically track that unconfined input to the Ellaville gauge. The Ellaville to Branford gauge. There's another one in the middle called
Dowling Park.
Dowling Park, thank you. That also has a long period of record, but so we didn't slice and dice the Suwannee as much as we might have. We can take the Branford and the lower Santa Fe gauge to the Wilcox gauge. That's the lower Suwannee. That includes the Ishtuckney, by the way. And then we can look also at the Santa Fe, Worthington Springs to the what they call the Fort White gauge. So we basically have 4 reaches where we can think about this flow gain. What does that look like? Well, first of all, it's stochastics. It's a lot of variability, right? So what you're seeing here is the blue line in each case is the downstream flow, so the bottom end of that reach. The red line is the upstream flow, and the black line is their difference, adjusted for the transit time, which is about 2 days for the pressure wave to propagate from one to the next. So you can see it's pretty heterogeneous. There's times when the flow gain is really high, there's times when the flow gain is negative, and it's kind of all over the place. And so let's unpack the statistics of this a little bit. So focusing on the middle Suwannee reach, again, that's the same graph, upstream and downstream data. We can kind of zoom in on a period, particularly dry period in North Florida, where you can see most of the time, the blue line, the downstream gauge is above the red line, which is the upstream gauge, which means that there was flow gain. But there are periods of time quite regularly when the red line peaks up above the blue line, implying the loss of water. There's a couple interesting things. There's a bunch of features here where the storm basically doesn't quite generate a reverse. It kind of slows the water down to 0. And we think those are periods of time when brown water gets circulated into the spring run, but it's not actually literally flowing into the aquifer. Post almost every single flow reversal is a rebound, right? So you push all this water into the aquifer, and then as the river recedes, that stored water moves back into the river, and that's the period of time when the oxygen concentrations are for persistent periods of time quite low. And so that's sort of a high resolution version, but it's probably easier to visualize it this way. So this on this axis now is the log transformed upstream flows, the flow coming from the upper boundary of the reach. And this is the flow gain. And what you can see is basically a flat line up to, somewhere on the order of 100 cubic meters per second before it starts to bend down. And so this is basically, these are the reversals, right? They occur at high flow when the river stage is way high, and that basically pushes water into the aquifer. And most of the rest of the time, they're pretty flat, right? So the vast majority of days, the flow gain is normal springs flow, springs discharging to the river. And under these high flow events, we see both an increase in variance, right? You see this plume is getting larger, and that's because at high stage, you can either be pushing water into the aquifer or it can be pushing a lot of water back out of the aquifer. But at really high stage, you're basically always negative. Look at the PDF of that. So this is just a frequency histogram, right? The median value here, or the mode is somewhere, this is on a log scale of days, is somewhere on the order of 22 cubic meters per second. So there's normally about 22 cubic meters per second of flow gain between the upstream and the downstream, but there's a pretty wide distribution and a lot of days when there's a substantial amount of water that's being pushed out of the river. That's how the Suwannee works. So So that number, 22 cubic meters per second, is kind of a useful number to keep in mind. And then this number is basically saying that the negative flux, right, the negative discharge, negative flow gain occurs for about 10% of the days. All right, so the question is that changing? All right, so before we get too far into that, I want to just take a moment to say, look, is this valid? Like, does it align with any other way that we think about this? There's lots of different ways that we can do this, but by far the best way, in my opinion, is to leverage an enormous human capital effort to observe the springs. So there are 7 springs at which DP park biologists go and look at the spring every single day, right? They put eyeballs on the spring, they make a designation, and this is their designation. Level A, clarity score 1, is basically like what we expect, clear water. Level 2 is okay, it's not great, but it's still clear. It's normal groundwater clarity. So we're going to call those normal flow conditions. Levels 3 and 4, tannic water, either like really tannic or less tannic, but definitely not reversing. And we call them brownouts. And then these are reversals, right? And so what we tried to do was to map the flow gain, which basically says, was it minus, what was it, negative? Was it near zero? Was it really high? And so reversals are basically easy to define. As any day where the discharge, the flow gain was negative, that was a reversal. Brownouts are basically defined as, okay, well, it was positive, but we were in the middle of a flood, right? And so that's flow gain was positive, but the discharge was pretty high, above the 80th percentile. And then this is a little bit new, but we also identify these periods of time when the discharge is positive, the flow gain is positive, but it's really, really little. It's almost not flowing at all. There's almost no springs discharging. We're calling those slack water days, and I'll explain the significance of those a little bit more later. But we applied, so this is one definition of the state of the spring. The other is our flow gain analysis, like the flow gain metric. Is it negative? Is it positive? And we assessed the correspondence between those two things, and it did great. The overall accuracy is sort of in the mid 80s in percent. We get the proportions of these river intrusion events almost exactly right. They're right around 1. The odds ratios that we can call, that's this right here, the odds ratio that we can call a dark day is 20 to 200 to 1. In other words, we're doing really, really well at picking off the days that the park biologists say there's something going on, and the flow gain analysis is saying something's going on too, right? The alignment between those two is really strong. So we feel really good that this is a way that the park biologists weren't doing this back in the 1930s. They started this in 2013, but because they aligned over the time that we have, now we feel like we can go back fairly confidently to 1931 and say something meaningful about the reversal incidence. Another way to validate that is to look at the proportion of normal days, the proportion of brownout days, the proportion of reversal days versus the predicted normal days, predicted brownout. So that's what this graph is showing, basically, again, saying that the alignment between the sort of different categories is pretty good for the springs where we have data. Gilchrist Blue, the park biologist goes out there, but the number is only like 200 days of data. It really wasn't enough for us to do. And this gives us some interesting thresholds of what constitutes a brownout in a river. So I think in the interest of time, I'm going to skip talking about this, just to say, this is a time series of the upstream flow, the flow at the upstream boundary. This is from I think this is from the Santa Fe River. The brown is when the park biologist observed a river intrusion event, and the orange is when the flow gain analysis says we observed some kind of river intrusion event. And the correspondence, I think, you'll visually is pretty compelling. Like there's some pretty important misses, but not enough for me to say, all right, I'm not going to feel very confident about this. Like the other method that Bobby Hensley and I did, if you told me that you didn't believe that paper, my feelings wouldn't be that.
Bobby, if you're watching, sorry.
We tried our best, Bobby. We really did. We did what we could. All right, so this is what it looks like for each one of the springs, each one of the reaches, the base flow gain. That's basically this value, 37 cubic meters per second in the upper springs reach, 22 cubic meters per second in the middle reach, about 42 in the lower reach. That includes the Ishituffin, which by itself is 10. And then this is the Santa Fe run, basically from Worthington Springs down to the Fort White gauge. So this is basically allowing us to predict the spatial or distribution of springs flows. And so we looked at where we have an estimate of springs flow for each one of those based on their magnitude, right? Each one of the springs has been designated a magnitude. And so there are 4 first magnitude springs in the upper reach. There's 20 second magnitude springs and 15 third magnitude springs. So that's what the histogram is showing. If you sum up the sort of estimated discharge of a first magnitude, all the first magnitudes, all the second magnitudes, all the third magnitudes, you get an estimated, you get an observed flow gain. That's this black line. And then you plot what we estimate from our flow gain analysis, and they correlate really well. In fact, the correlation coefficient between those two is 0.99, which I'm going to say is good. I'm going to go forward with that one. I'm happy with that. Don't change anything because it worked really well, right? All right. So now hopefully I've instilled some confidence in the method, and let's start talking about what we're going to do with it. So the main method that we're using is something that I'm calling cumulative anomaly analysis. This happens, people in climate science do this a lot because you have very noisy data from which you're trying to extract some signal that you don't want to convey all the noise. You want to sort of convey the mean behavior. So cumulative anomaly analysis is basically saying, look, if I take the cumulative time of some phenomenon, each day I add a day, and I plot the cumulative count of that phenomenon. That could be, the number of days versus the number of papers that David writes. And like, it's just this astronomically steep straight line. But in the early phase of his career, maybe he wasn't publishing so much. He went through this inflection point where he was really kicking ass, and then he got full professor and just decided to retire quietly.
Yeah.
So cumulative analysis that basically allows us to sort of investigate something that on average is sort of doing the same thing, but we want to look at the temporal anomalies. And so if we took the residuals between this fitted line, which is David's average productivity, versus the black line, which is cumulative total productivity, we get this, this big dip in the beginning when he was just getting everything started. And then, this big peak and then tenure or what? Yeah, 12%. The beauty of this method is there's no arbitrary window for detection. We're not imposing decades or 5-year windows. And basically, we can look at it every year as an anomaly, and it allows us to sort of detect cycles. It also allows us to. So this is a cumulative incidence over time. But if instead of time, I put rainfall. So I did cumulative rainfall. Every day I take the rainfall that I got and I add it up and I plot that against some hydrological response. In some way, I'm controlling for the climate signal. So now I can isolate the effects of these hydrological behaviors independent of their of the rainfall signal, which I think is important. So we have this period of anomalous increasing in frequency. So when the slope is up, the thing, David's publication rate is increasing. When the slope is down, David's publication rate is declining. I'll stop there with the announcement.
Yeah, Ben's ass is watching this as well.
Yeah. Hey, Ben, he's awesome.
Yeah.
Do not do anything to let David. So then, like I said, you can index terrain to control for climate forcing and hopefully isolate sort of non-climate drivers. So what does this look like in principle, right? Okay, in sort of hydrologic, not cartoon version. We have some rainfall input. This is the daily time series of rainfall from Lake City. In the end, I used monthly rainfall data because Lake City doesn't represent everywhere all that well. And we don't have any other daily data, but anyways, this is the daily time step. This is the daily time series of flow in the middle Suwannee. Now we can plot the cumulative days or cumulative rainfall versus the cumulative discharge. So the blue line is versus cumulative time. The red line is versus cumulative rainfall. And we get a line. Right, we can fit a line to those data, and you might say there's no residuals. They're not very interesting. The residuals aren't all that much. But if you look at the residuals are actually quite interesting, right? So this is the residuals of, this is actually just for rainfall. So cumulative time versus cumulative rainfall. You can see this long period wave right here, right? That's very consistent with the Atlantic multiplicadal oscillation, right? Peak rainfall in the early 1970s during the warm phase of the AMO. This long period of drought that's basically the trough of it was in late 2000s, 2005, and then this recent recovery in rainfall. And so this cumulative anomaly, in fact, that's how the AMO was found, was using cumulative anomaly analysis. So we can see that in the rainfall data. If we look at the flow data, this is the flow data coming in. This is actually the flow data at the Ellaville gauge, the upstream part of the middle Suwannee. We can see one is where we do rainfall correction, and one is where we just look at the raw data, so versus time. And I think you'll agree there's not really much of a difference to speak of, right? So there's not a strong rainfall signal embedded in this, otherwise there'd be divergence between these two lines. But the thing that really stands out is that starting in about 2000, the bottom fell out of it, right? We're not getting any, the accumulated flow has this massive anomaly that starts in the late 1990s, propagates all the way to today. That's basically diagnostic of less water coming in at the upstream boundary. This isn't water from the aquifer. This is water from the rest of the watershed. We can do that. This is, I'm not going to spend much time on this. It's just there's multiple ways to think about this line. I can think about this line up to a breakpoint and fit the line there and then calculate the anomalies, or I can fit the line globally. And basically there's a little bit of a difference, but we're not going to fuss with it. So we're basically in all of these cases, we just fit a line to all of the data and then calculate an anomaly from that. So we have a couple questions that we can interrogate. We got this flow gain time series where we know the flow gain every single day. And now we want to sort of ask some questions of those data based on this analysis. The first one is rainfall and upstream flow stationary. Basically, this includes the total rainfall, which I've kind of already shown you, large storms, floods, and upstream flow, like the flow coming off of the confined part of the watershed. We can ask whether springs flow is stationary. In other words, does the time series of the discharge under normal flow conditions from the springs, from the aquifer, has that been basically stationary or is it declining? And then, of course, the reason that I started on this was that whether the incidence, duration of reversals, brownouts, and slack water flow states are stationary, right? In other words, have they exhibited some significant divergence from normal historical conditions in the recent period? Just to give you an idea, there's a lot of geographic heterogeneity in these reversal dynamics across these different parts of the Suwannee. So the reversals are most, like the Santa Fe River in particular, basically doesn't reverse. 1.6 reversals per year, total of about 5 days per year on average, that you get reversal conditions in the springs of the Suwannee of the Santa Fe River. That's because the Santa Fe River has an extra special bladder that holds on to floodwater in the sink rise system. So all the floodwater, before it can get to the lower Santa Fe, it has to go down underground, mix up with all the groundwater down there, and that basically cuts the top off of a lot of the flood. So the lower Santa Fe doesn't flood like the rest of the Suwannee does. But we can see the sort of duration, the dark days duration, somewhere on the order of 60 to 80 days a year in the middle Suwannee. Slack water days, 40 to 30 to 50 days a year. So these are useful benchmarks. This is like the normal conditions, the average over the last 100 years. So the first question is whether there have been anomalies in rainfall. So you can see again this sort of AMO signal, right? There's this long period, 30-year frequency behavior. It's not uniform, right? So it's much more prevalent in sort of northern part of the Suwannee and less so in the southern part. One of the things that was really interesting is that the incidence of these large monthly rainfalls, like this is basically monthly rains that are greater than 240 millimeters, 24 centimeters, has really increased since 2010. I think that's really associated with tropical storm activity. We see lots more of those. And so the significance of that is, I think, remains to be a little bit sorted out, but it's certainly a clear recent change in the climate regime that we're observing around these gauges. Now, all these data are from PRISM. So these are synthetic data in the sense of being interpolated from radar data. And so there's, whatever. People bicker about the source of the rainfall data. It's PRISM data. So rainfall is generally stationary. Like one way to see that is that the ending case is basically the long-term average, right? We end up in all cases right around the x-axis, which means that they ended up where they started, more or less. They're staying more or less average. There's some long period cycles that are probably super relevant to understanding the incidence of these events. And there is this recent increase in storms that may be significant for something. What about the hydrologic anomaly? So what this is showing is the cumulative upstream floods. This is the number of days that are in a flood. This is basically how many days is the discharge above the 90th percentile. And you can see the floods are declining markedly. Now, I just showed you that the big storms are going up and the floods are going down. So as a good hydrologist, you might be wondering, where the hell's all that water going? Good question, I don't know. But that's a really important divergence in the data here that I think merits some attention. Needless to say, the most important thing right here is the discharge coming from the upstream parts of the watershed, which round about 1995, maybe 1998, basically falls off. right? So the cumulative discharge, like typical discharge from the watershed is on the order of about 20 centimeters. And between 1998 and 2022, which is when we ended this data, each one of these places is missing somewhere on the order of 6-7 years worth of flow over that 25-30 year period. That's a lot of missing water, right? You can put that in other terms, cubic kilometers, however you want to do it, but there's no way to say it other than like we're getting way less water from the confined parts of these watersheds. They're generating less flow. And what is that? That's not directly anyway, Floridan aquifer pumping and Jacksonville and all that stuff. It's something else. There may be stronger connectivity between those, the flow generating mechanism in those confined regions and the Floridan aquifer than we think, right? They're a bit more coupled. But suffice to say, we're getting a lot. It may be land use change, it may be, changes in climate, it may be a whole host of things, but the signal is as clear as I've seen a demonstration that there is a real change in the hydrologic regime. So the clear and large recent declines in floods and flow. The cumulative flows are basically the upstream inputs, and they have declined markedly. The one that I think is the most troubling of all of the results I'm going to show you is the anomalies in the flow gain. So now we're talking about the springs flow, right? The flow from the Floridan aquifer to the springs. This is the thing that probably most of the water management districts, as they set MFLs, are most concerned about. And so we can think about that in terms of the flow depth anomaly. We can think about it probably even better in terms of this is the low flow, this is the cumulative total gain, right? So we see this decline in total gain. Total gain basically includes both the times that the river is gaining, the river is losing water, and the times that it's rebounding. So try to get rid of all those. It's what we call low flow gain. And so low flow gain is basically all the water that we would consider like normal springs flow. Right? That's the water that comes out, the blue water that comes out of the springs. And starting again in the mid 1990s to 2022, with the exception maybe of the middle Suwannee, which seems to have turned things around for reasons that I don't totally understand, but we see this large decline. So basically, if you sum all those up, we've lost about 14 cubic kilometers of aquifer water flow to the Suwannee River over the last 25 years. That works out to about 18 cubic meters per second, which if you're doing the math, that's something on the order of 6 missing first magnitude springs through the Suwannee system. Right? 6 springs, if you take 6 first magnitude springs, turn them off, that's the equivalent to what's going on in the throughout the whole Suwannee system. And I think that's pretty troubling, right? We don't have very many springs where we have flow records, and most of the springs where we do have flow records are these big iconic springs like Ishtuckney and Rainbow and Silver, where there have been periods of time when the flow has declined markedly, but overall, they don't show this magnitude of a signal. And so it's these small, less well-known springs, the ones that reverse, the ones that are probably most proximate to things like agricultural pumping. Those are the ones that we're seeing really dramatic declines in discharge. The reversals and brownout story is like super confusing. There are some places, so this is the cumulative number of days, the anomaly and the number of days that we see reversals. The Santa Fe River is down here in blue. It doesn't change at all because there's no reversals in the Santa Fe. It just doesn't really happen. In the upper Suwannee, this think about Madison Blue Springs and something that, what used to be White Springs, that area is seeing this systematic increase in reversals really since the 1960s. That's this red line right here. The lower springs, this is Manatee, Fanning, Little Fanning, Otter Springs, all the springs along the lower Suwannee, like they have seen this almost, unbelievable increase in the incidence of reversals. Like the notion is that those springs never reversed before, and now they reverse all the time. Fanning Springs is dark most of the time I've ever been there. And so this increase sort of comports with, eyeball tests, but this is a big change. But then here we have the middle springs. We're thinking about Troy Springs, Lafayette Springs, Little River. Like this actually, the incidence of reversals is declining. So there's some like interesting geographic heterogeneity that I don't really understand yet, but there it is. The brownouts are consistently declining, which is super surprising to me because the people anecdotally describe the springs as being brown much more often. That could be that our definition is wonky and wrong, right? We've tried a bunch of different definitions. This really doesn't change that much. suffice to say, right, starting in the mid 1990s to today, the incidence of these brown events has actually declined, which is a mixed result, and I don't 100% understand it. We definitely think from the work that Sam Halley has done that the brownouts are way more significant ecologically than the reversals. They happen more often, and the duration during which like they basically turn the lights out and shut down the oxygen supply to the ecosystem is longer and more severe. And so the brownouts we think are probably more consequential for understanding ecological change. And if they're going down, then hey man, we're doing a great job. So if we look at the total dark days, it's really mixed bag, but then started looking at the incidence of these slack water events. So a slack water event is sort of like when the spring turns into a lake, right? It's not flowing very much. It's just standing. The flow's not going into the aquifer, but it's not coming out of the aquifer either. So you basically just have stagnant water. And so Nathan and David and others have been exploring this hypothesis that these low velocity periods are super important for the establishment of filamentous algae. These would be the periods when the flow velocities are low. The incidence of that has increased markedly. It's also a period of time when the gas exchange, right, the rate at which oxygen enters the water slows dramatically. So you get much more likely conditions of hypoxia. I think that's a hypothesis more than a statement of fact. So there's mixed dark days, way more slack water days, and that has, you think, important consequences for understanding how these ecosystems are going to be responding to flow and have been. All right, so summary implications.
But we have questions, so yeah.
So basically, this is like a little bit of a time machine. Like we can use this technique to interrogate the flow in ways that I've never thought about before. In fact, I should introduce Annika and Chao. They're two visitors from Germany sitting in the back of the room. Chao is going to be taking this idea of flow gain and trying to sort of extend it to rivers everywhere, right? Anywhere we can get data. And so this flow gate analysis, I think, is a really cool way of thinking about it. For the Suwannee River, it's especially cool because we have this 90-year record of reversals and spring flows that reveals to us probably not a rainfall signal, right? There's not a lot of change in the rainfall that would explain the observed changes that we're seeing. We see this really marked evidence for spring flow declines, and also sort of contemporaneously evidence for the decline in the flow from the upper parts of the watershed. So the flow generation in the Suwannee River in total has declined really substantially. There's increased incidence of flow reversals in the upper and lower Suwannee, and the middle Suwannee is behaving a little bit differently. And this really dramatic incidence in these periods of time when the springs are actually more like lakes. And since there are these impacts of reversals and slack water periods and all the rest of them on metabolism and plant community structure, I think these data are germane to the setting, establishing, testing of the minimum flows and levels, which is, for those of you who aren't from Florida, the minimum flows and levels are equivalent of environmental flows. So there's a flow regime that would protect the ecosystem written into statute into Florida code. And so that is our case now to the water management district, is to pay attention to these things as part of the designation of those MFLs. So that's that.
All right, let's give Dr. Cohen a round of applause. All right, so we'll take questions from the room, and I will see if we have any on YouTube. So we'll start with students in the room with a question or visiting scholars. Dr. Cohen. This is the part where the professors wait. We wait because we have our questions. We're going to give you all one first.
It's pretty hard to unpack all of this tonight, but I'm still fixing on frequency as a variable, the frequency of these dark water and things. And it appears that you addressed that. Could you elaborate a little bit more on it?
Sure, yeah. So there's multiple different ways you can think about the severity of a reversal. So the frequency, like a reversal regime, it would be the frequency, how often does it happen? It could be the total duration or the average duration of them. It could be the magnitude of the reversal, like how much water. And it turns out that those are all super correlated to each other. So everything that you saw was just about the duration, and the frequency and the duration are super strong. But it's a good question because it becomes a permutation problem. I have all these reaches and all these metrics, and then I have like 600 graphs to try to share. And so I should have said, they're all basically, all the various metrics of reversal severity are correlated strongly.
So you only share 200.
Yeah, exactly.
Yeah. All right, so we'll give you off the hook, because I really want to ask this question. So you kind of just, maybe you didn't mean to, but sort of poo-pooed the idea of pumping. You said the big floods are getting more and the rain's kind of coming back. The spring flow continues to be at this deficit. And so I don't know, can you talk a little bit about pumping versus maybe ET, or maybe at least tell us like 18 cubic meters per second as a loss
Yeah.
relative to, like, how do you answer the many straws question from Dr. Knight? You know, like, how does 18 cubic meters per second compare to pumping withdrawals, which are not 100% consumptive, but
Right.
kill that bird, you know, whatever.
Right. So I think
Well,
that, so 18 cubic meters per second is about 450 million gallons per day. We'll just do, you know, most people think about pumping in millions of gallons per day. Except our German. So 1 million gallons per day, 400 million gallons per day is so much higher than the cumulative net withdrawals of from the agriculture in the Suwannee Valley that it's like.
Like an order of magnitude,
Yeah,
or
roughly. I mean, it's like, I think it's 5 times higher or something like that. And so I mean, I think those numbers, we haven't done a whole lot to compare them. And the ET changes, it just, first of all, ET didn't change overnight in 1998. That's not what happened. And so I don't think that's what's going on. I think one plausible explanation, or maybe not the most, one plausible explanation has to do with the migration of the saltwater interface that Hockey and Jim Jowitz and others have talked about. And that would help explain the magnitude and the lags that are observed in this. There's no way to validate that because we don't have any sensors that are 500 meters down measuring saltwater movement, but the volumes that you need to invoke in order to just explain these changes that happen, they're just huge. Invoking far field pumping, you know, maybe you get a little bit closer. The total consumptive use in Florida, the net consumptive use is like 2 billion gallons per day. So we're talking about 25% of all of the Florida's pumping is realized in just the springs changes here. You know, they're mismatched in terms of their magnitude. That doesn't mean it's not contributing. It almost certainly is, but I think in order to close mass balance, we have to have some other explanations for why the phrase.
good to, I think just good to address those magnitudes. Yeah. Probably.
So is the nutrient loading story with regard to like environmental impacts of spring, is that kind of a red herring? Is that, I just noticed he didn't.
You asked the right there.
That question, in my opinion, yes. It's not to say that mostly, well, whatever, I could go on about this for way longer than you guys. But everything we've done has basically suggested to me that the nitrogen that was supplied to these ecosystems under historical conditions was more than adequate to satisfy the demand of autotrophs and heterotrophs, and that increasing the supply of a non-living nutrient shouldn't have any effect. And that explains why there's no correlation between water trait and ecological change. There's more to it than that.
Yeah.
But that's a good summary. Yeah, AJ.
So you've got this deep, who knows why, but spring flows are decreasing. You're getting more frequent reversals, less frequent brownouts, but also we're expecting more intense, more extreme precipitation events moving forward, right? So if you were able to fix one of those problems to reduce, like, what are you more concerned about in terms of causing brownouts, reducing springs or increasing flooding?
I think it's a good question. There are two sides of the same coin, right? Like you get reversals because the aquifer is lowered and doesn't resist as much, and because the floods are higher magnitude. And so I'm not sure it's straightforward to say that one or the other is a higher priority. One or the other may be easier to fix. I think we probably have more leverage over the springs flow as a just, you know, operationally, regulatory wise than we do over the generation of floods. So that's probably that's the lower hanging fruit, if that makes sense. But yeah, I think it's the coupling of both of those that makes the phenomenon happen.
All right, I know we're a little bit after, so if you have to go, you can quietly go. However, if there are other questions,
Well, Nathan's going.
go ahead, Nathan. Yeah. Only if you have a class, you're permitted to, yeah.
So you mentioned like a saltwater interface, or that would really like explain stuff coming from flows from the aquifer, spring flows, you also said that the confined region is experiencing declining flows as well, so. And is there, do you have any hypothesis for that, or?
I do, I mean, so I think what might be going on is that the connectivity between the flood generating parts of the watershed and the Floridan aquifer are stronger than we like operationalize the way we think about it. We think about like the confined region, basically no water goes down, it only goes into surface water. And then the only place where the aquifer comes out is in the unconfined. And I think if there, I mean, and we know, for example, that there are thousands of swalettes, places where the confining unit is perforated and stream water goes pouring down into the aquifer. And we know that people are pumping water out of the ground underneath of the confined unit. And so I think that there's the coupling between the superficial aquifer processes and the Floridan aquifer are quite strong, maybe stronger than we've thought. And that's why you're seeing less flow coming off, is that there's a manifestation of the declining head in Florida underneath the confined, underneath the confining unit, and that's basically allowing more water to be accepted by those swalettes. I don't know that for a fact, but that would also, by the way, help explain why it is that the oxygen concentrations in a lot of the aquifer are declining, because basically we're propagating a lot of dark water would have just run down the Suwannee and out to the Gulf. Now it's going down into the aquifer and it's being, mineralized, consuming oxygen along the way. And so those two things may be.
And you said that there wasn't any change, like real change in rainfall over the time. What about, and did you look at like recharge or just like rainfall distance? So like you just look at the rainfall signal or like the rainfall minus the potential evaporation signal?
I did try. I mean, I didn't get it. I didn't get fancy. I sort of actually more or less did the minimum, right? It's either the rainfall or the ET is either the rainfall or it's either PET or the rainfall.
Right.
And I did that and I made so that's a toy recharge model and it really didn't change. And that's partially because I think PET is in North Florida is just like, it's kind of like a heartbeat and it doesn't vary that much from time to time. So, but I would like to do more of that because I think that could be, especially since you think that ignores any change in land cover. And we've got some data that's completely separate to this, but suggesting that since the 1930s to today, forest cover has like basically more than doubled, right? In 1938, forest cover was about 35%. And by 1990, it was like 90%. And so that's a major land use change. Of course, it's not really consistent with like a step change,
Yeah.
But it is consistent with an overall decline in water availability.
All right, let's give one more round of applause to Dr. Cohen. Next week, we will have, for our seminar, we have Erica Hernandez from the Alachua Conservation Trust, another alum from the center, and she will be live here in person. So we'll see you all next week. Thank you, everyone.